A apresentação foi organizada pelo Student Chapter aqui da USP. Acho que todos estão familiarizados, né? O Student Chapter é um grupo de estudantes aqui, acho que agora só da pós-graduação, que tem um interesse em geologia econômica. Estamos vinculados à SEG, né? Society of Economic Geologists, e estamos organizando sempre essas apresentações. Estava tudo meio corrido, a gente não conseguiu organizar muitas esse semestre ainda, mas começamos aí com o pé direito. Temos o Fernando Tornos aqui e o Diego conseguiu trazer ele para falar para a gente. Então, apresento vocês o Fernando Tornos. Ele vai falar para a gente hoje sobre o cinturão piritoso ibérico, por que ele é um VMS, e acredito que estamos todos muito curiosos. Fernando Tornos, thanks a lot for coming. So, let's speak in English then, right? Em inglês para todo mundo, acho que todo mundo volta para inglês.
Well, Diego invited me to come here after the meeting, and he told me your favorite. I suggested him some different talks, and he suggested one of the Pyrite Belt because probably it's the most unknown district for people in South America. Well, the Pyrite Belt, let me see how this works. Yes, for people who know it, and many people in Spain don't know it. I mean, it's something really amazing from the geological and historical point of view. I mean, it's the largest concentration of VMS deposits in the world. In fact, it's the largest sulfur. The oldest slags are about 2.8 thousand years. The Tartessians, in fact, the Pyrite Belt is one of the few districts in the world is quoted in the Bible. They talk about the gold that comes from Tarsus, and it was these people traded with the Greeks afterwards, and the Phoenicians, and afterwards the Greek came. But the real important story of the Pyrite Belt starts with the Romans. Romans knew perfectly what they wanted to mine, and they went directly to the gold and silver-rich ores, usually in the base of the Geociências. The Geociências have, in the lowermost part, a thick zone with very high-grade silver and gold grades, and Romans knew perfectly that. The Roman Empire finished, and the mining just disappeared there. And in fact, in 1556, King Philippus II sent an expedition to try to find the mines that were in the Bible, and they found a complete description how these people found the huge Roman caves and so on, but at that time, obviously, having all the metals from America, they were not interested. In 1850s, Spain came into one of their several bankrupts, and they sold the mines to a British company. And it's where the Rio Tinto mine, the Rio Tinto all over the world, was created. And they started mining Rio Tinto and Tarsus. And then started a huge boom of mining. They started with the cementations, high-grade cementation, copper-grade ores, then moved into the gold in the Geociências, and finally into pyrite, as I said, for hydrosulfuric acid. And this hydrosulfuric acid was one of the bases of the industrialization in Europe. As I said, the pyrite started to decline. People were no longer interested in pyrite, mostly because it was much cheaper to obtain sulfur as a byproduct of the oil industry. So slowly, all the pyrite mines started to stop. And then they realized that with the pyrite, there was sphalerite, galena, and chalcopyrite. So mining moved into the base metals, polymetallic ores. And that's more or less the situation today. Today there are 7 producing mines. You have the names there. There are 3 projects going on. They will start probably in the next months, and 4 projects developing. So, as you can see, the evolution in the Pyrite Belt has gone from gold to silver, Roman times, copper in the British times, pyrite, then base metals, and now people are looking around, and there are some targets for cobalt and gold. And in the last, let's say, couple of years, there is some interest with this, what's called the critical metals, and try to evaluate if the Pyrite Belt has resources of critical metals such as indium, gallium, and so on. key things you have to remember before going ahead in the Pyrite Belt. First, tectonic control is an intercontinental marine basin that has, in the classification of VMS deposits, a felsic-silticlastic sequence. Second, the district, you will see the size is really small. It's 100 kilometers or 30 kilometers. The thickness of the volcanic rocks is really also small. It's less than 2 kilometers. So that's not a lot for a volcanic sequence. And the time span is really short, less than 20 million years. So a lot of things happen there in such a small space, in such a short time span, to produce this huge amount of sulfides. And another important thing, there are two events of mineralization. One, in the southern Pyrite Belt, is strictly confined to the Devonian Carboniferous boundary. So exactly, the Devonian Carboniferous limit is where all the massive sulfides take place, and is always related with shale. And the second group is much younger, about 20-30 million years younger, and it takes place in volcanic rocks of the lower early Tornasian. Clear up to now? Nobody complains, okay. Well, the stratigraphy it's very easy, the general one. We have a basement, it's a typical continental shelf sequence with shale and sandstone. And it's very monotonous, 2,000 meters below the volcanic rocks. And just in the contact with the volcanic sequence, things start to change. We have a huge of debris flows, we have delta phases, something limestone, something that indicates that the basin is changing. The basin is changing. Then we have the volcanic sequence. It's mostly, well, as I said, mafic and silicic volcanic rocks with chemical sediments, and above it is what's called the Kulm group, is in a synerogenic sequence. So the volcanic rocks, the green here, are the ones that host the massive sulfides. Good. No, sorry. Well, that's a map of the Pyrite Belt. Look, the size is really small. In, let's say, in gray, it's the volcanic complex that hosts the massive sulfides. So, well, reference point Seville is close to the LC, to Las Cruces, and that's the Atlantic Ocean, so it's really, really small area. As I said, tectonic setting, it's probably a pull-apart continental basin. There is a big debate now if we are talking a back-arc basin or it's a fore-arc basin developed between 360 and 307 million years. That's nothing for Brazil. It's a typical thin-skinned foreland folded thrust. That means a lot of thrusts, low metamorphic grade, and a really complex sequence because you have always thrusting. So you never know which part of the sequence are you, because there are hundreds of small thrusts, one above the other. And probably all of this is related to the oblique collision between Gondwana and Laurasia in Variscan times. Volcanic rocks, as I said, obviously in VMS districts, they are related to volcanic rocks. The dominant ones are felsic, dacite to rhyolite. A big debate about these rocks, what's the origin? As you know, if you have glassy volcanic rock made of glass, you demitrify it, then the genesis, metamorphism, and deformation, that produces a huge amount of complex textures. And everybody discusses about the origin of these rocks, usually called tuffs, and that means everything. Like the word tuff means, I don't know, it's a volcanic rock and I don't know what's that, more or less. But basically now what we know is that there are domes and cryptodomes, that means domes that never go to the surface of the sea, they just get subvolcanic emplacement. When they come to the surface of the sea, they produce sometimes explosions with pumice rich mass flows that go lateral to the domes. That's the classical phases in the felsics. While the mafic volcanics, much more restricted, are basically flows and seals. If you want, I can give you the PDF afterwards of this, or I mail it to you. Well, that's the classical interpretation, one interpretation of the Pyrite Belt. A dome and the VMS deposits, remember, we have two positions. One close to the Devonian Carboniferous boundary, and upper one in the upper part of the domes. The lowermost ones, Los Frailes or Anacoya, are located in the Devonian Carboniferous boundary. Remember, the uppermost ones are the lower Turnesian. Geochemically, well, if you read most papers on the Pyrite Belt, you will realize people talk about bimodal volcanism. It's the flavor. I mean, everybody wants to find bimodal volcanism. However, here it doesn't look very bimodal. It looks like a rather continuous trend between basalt and rhyolite, and some of the rhyolites are really, really high in silica, up to 80% silica. So it's quite a strange sequence. But most of the rocks are highly altered, so it's really difficult to classify them. Since they are volcanoes, there is a lot of seawater. As you know, seawater melt interaction that produces widespread spiritization and alteration. So you have to use immobile elements to classify. But basically, let's say, remember the felsic, the underside to rhyolite are classical low aluminium, high terbium calc-alkaline sequence, typical of magmatic belts or back arc basins, while the basaltic rocks are alkaline to tholeiitic, typical of spreading areas. So the model people assume here is usually you have extension in the back arc basin, ascent of mafic melts, they melt the crust, and then you have the felsic melts. It's a classical process in exceptional environment in magmatic arcs. What we have used is the, let me see, people that love these fancy things. What we have seen is something opposite to what you see in most districts. In most districts, people say high zirconium volcanic rocks are related to mineralization. And probably, I'm sure you have read that. As a guide to exploration, the argument is the solubility of zircon in felsic melts depends on the temperature. And the heater is the melt, the more chances you have of producing convective cells and forming mineralization. However, this seems not to be the truth in the Pyrite Belt, since surprisingly most of the ore is related to low zirconium, that means below 200 ppm volcanic rocks. So we have in the sequence, high zirconium volcanic rocks are not mineralized, low zirconium volcanic rocks are the one mineralized. Geochemistry is critical for us for trying to understand the rocks. It's because without geochemistry, you don't know in which part of the sequence you are. You have huge amount of breccias, volcanic breccias. All of them look very similar, and the only way of tracking where are you is by immobile elements: zirconium, yttrium, titanium, and aluminium. Basically, the ratios between these elements is what define where are you. So if you're working with altered volcanic rocks, these things of immobile elements are really critical. And in the top of the volcanic sequence, there are some strange oxidized sediments that include a huge amount of small manganese prospects. In fact, some people say that the Pyrite Belt should be called the manganese belt. I mean, it's hundreds of prospects of chert or jasper with interpreted manganese oxides. Obviously, now no mine is open because they cannot compete with the huge deposits in South Africa and so on. Remember these rocks, we will use them for the numerical modeling afterwards. Well, that's more or less the stratigraphy in the southern Pyrite Belt. In black is the massive sulfides. And they have been dated by microfossils, by palynology. And they, as I said, they strictly correspond to the Devonian Carboniferous boundary. There is something related to this boundary that produces huge amount of sulfides. The dates people in mineralogy call it the Strumian. It's the very, very uppermost part of the Devonian. It's less than 1 million years. In less of 1 million years, you probably form 1,000 million tons of massive sulfides. That's a huge amount of sulfur. Well, that's the northern part. If you go to the northern part of the belt and you go to the late Strumian sediments, they are absolutely barren. No hydrothermal alteration, nothing. But you find the deposits in the uppermost part of the belt. There are very few datations of these domes, but they suggest about early Tornesian, but quite above in the stratigraphy. Deposits in the southern part of the belt. There are really, really large deposits, but unfortunately, pyrite-rich, fine-grained, difficult to mine. If you don't like pyrite. As I said, they are in the contact between the PQ, late Devonian, and the volcanic rocks, early Carboniferous. They are beautiful sedimentary structures. Little doubt that these deposits were deposited in the seafloor. I mean, truly extract deposits, typical venting of, as you see in the National Geographic videos, of the black smokes coming out, and then the sediments, pyrite-rich sediments, deposited on the bottom on the seafloor. The problem, as we will see, is which type of seafloor is this one. As I said, this is strictly a very quick process, takes place in less than 1 million years. For example, in the Tarsis mine, nothing to do with the Phoenician Tarsis. It was called Tarsis because it was very, let's say, touristic or very fancy to call it like the Roman in the Phoenician mines in the Bible, but it's a very recent name. You have a stockwork hosted by shale of the PQ group, and here you have a huge chloride alteration. Interestingly, we will use that again afterwards, is enriched in sulfur-poor minerals. That means you have a lot of pyrrhotite, tellurides, you have gold, cobalt minerals that you don't find in the massive sulfides. Something happens here. There are minerals that are poor in sulfur. Let's say they're stable in low sulfur fugacities. Above it are the earlier most massive sulfides. In the very, very bottom layer, we have worms, remnants of fossils, not a very good or nice place where to live, but they live there. Then you have evidences of some oxidizing environment, remnants of hematite replaced by pyrite. You have sulfates replaced by sulfides. And everything suggests that when the very first fluids vented on the seafloor, it was an oxic environment. Afterwards, you get into the true pyrite. There is one strange ore called the carbonate ore made of siderite and pyrite. It's probably bacterial mats. The only way of forming carbonates and sulfides at low temperature in any system is by bacterial reduction of sulfates. If you find a rock that's made of carbonates and sulfides and you are below 150 degrees, the only way of forming that hydrothermally is by bacterial reduction of seawater. That means the sulfate in the seawater is bacteria transform the sulfate in seawater into H2S, and at the same time they transform organic matter or methane into CO2, and in that reaction they obtain the energy for living. And that increases the amount of CO2 in the system, increases the amount of H2S, and that produces the precipitation of siderite and pyrite. Following that, we have the contact. We have the uppermost part of the massive sulfides, beautiful sedimentary structures. I think everybody would agree those are sediments with graded bedding, with shale interbedded and so on. And then we get into shale. So shale, massive sulfides, shale, and only laterally there are some volcanic rocks. This thing, this couple of slides I showed you before makes us a small problem. If you follow what happens in present-day VMS systems in the oceans, most of these systems they vent into oxic seawater. No? So what happens is as soon as the hydrothermal system finishes, the sulfides are in contact with seawater, and probably in 30, 50 years, there is no sulfide mound. So people, now we have a rather long history of tracking what's happening with these seafloor mounds. When one mound stops, in 30, 40 years, it has disappeared, oxidized and disappeared. So that means that if you have an exhalative massive sulfide, you have to preserve that system, or it must be formed in an oxic environment, something that doesn't allow the oxidation of the sulfides. Where you can find that? Well, on one side you have one alternative. It's just a lava flow that covers the massive sulfides, and that isolates the sulfides from the seafloor. Another alternative, you're in an oxic environment. Where can you find anoxic environments? You can find them Black Sea, for example. You can find them in fjords, in inlets, something where there is very little renovation of water, or you have it in brine pools. Brine pools are accumulations of brines, of really saline fluids that they don't mix with seawater, and they stay in the bottom of the sea. So it seems to be a bit strange, but there are videos in the Mexican Gulf where they can see like masses, let's say like a ghost, made of extremely saline water that doesn't mix with overlying water. And it's just a brine having extremely high salinities. So probably if hydrothermal fluids vented on the seafloor and they are saline enough, they don't mix with seawater, they just displace seawater, but they keep the anoxic conditions on the bottom. Follow that? Okay. Well, how to sort this problem out? We did some biochemistry, and what you can see is that you see arguments for anoxia. The best argument for knowing you are in an anoxic environment is the shales are laminated. If shales don't show any lamination and they have a lot of bioturbation, that means the system was oxidized. If you have lamination, that means there was no life there, so that means probably it was an anoxic environment. And the second criteria is geochemistry. You will have huge amount of papers saying how to define an anoxic environment. Nobody agrees with the other people. What looks like is the vanadium content or manganese content are the best tracers of anoxia. And what we have here in Tarsis, we've made in several drill holes a sampling, is you have an oxic environment, low contents of vanadium, low content of manganese, and look, in red is the mineralization. When you approach the mineralization, the system shows an increase in vanadium and manganese. What means that? The system was oxic, was a normal ocean, and then something happened, the Devonian Carboniferous boundary, that increased the anoxia in the system, and as soon as the thermal system finished, we return to normal conditions. That's why these deposits are preserved. And that's why they formed. The best reason is to think that just hydrothermal fluids were getting into the basin. These fluids were equilibrated with deep rocks that were anoxic, they were saline, they did not mix with normal seawater, and they just formed an anoxic layer in the bottom of the seafloor. When the hydrothermal system finishes, system collapses, and you can return to oxic environments. But another important thing here is that, remember, exactly the Devonian Carboniferous boundary is that we've made a study of biomarkers, organic matter, in this shale, and what we find is that just in the mineralized horizon, there is an increase in two things. One, bacteria, not surprising. We need a lot of bacteria to produce those massive sulfides. And second, we have a lot of indicators of vascular plants. That means trees. Something is happening that's bringing a huge amount of debris from the land, is destroying woods and bringing organic matter from these woods into the sea. Probably that's what bacteria ate, organic matter to produce CO2 and H2S. Well, we are in the Devonian Carboniferous boundary, and strictly the limit, and as I said, the onset of volcanism in the Pyrite Belt. So if you drink a couple of beers, perhaps the alternative is, well, if we are starting, imagine a land with a lot of trees, there is volcanism, there is acid rain, destruction of the trees, the organic matter, obviously it goes into the sea. That organic matter in an anoxic bottom is a perfect place for bacteria to live. So the bacteria had huge amounts of food, the organic matter coming from trees. They had the hydrothermal fluids coming from the seafloor with a lot of iron and metals. So it was the perfect place where to live and to form the massive sulfides. Only 30 million years younger. Let's go to the northern Pyrite Belt. Well, here is a map of the Pyrite Belt. You see some of the deposits for VMS. They are rather big. We're talking about almost 800 million tons in Rio Tinto. It's quite big for being a VMS. And here things are absolutely different. Look the morphology of the massive sulfides there. Very strange, intricated things. It's difficult to explain by folding. It's morphology. Into felsic volcanic rocks, no shales, no sedimentary structures, just volcanic rocks and replacement of the volcanic rocks. Nothing to do with the previous stuff. Sometimes even the stopeworks, the feeder zones, as you can see. Does it work?
I think that's the control of this. Do you want to point something, Professor?
Yeah.
Use the stick there.
Which one? Sorry? Well, the stick.
Yeah.
Probably, much more.
Probably better. Yeah.
I don't know if I'm very used to this. Beautiful bamboo. Okay, look here. You have a stopework. That means some massive sulfides cross-coats by veinlets of sulfides. In any place you will say, oh, this is the feeder zone. The thing that's coming from the down part of the lower part of the VMS, and it's going to arrive to the surface and form the massive sulfides. But this looks like a fragment into pyrite. How can we explain that? Look here, the contact. This is a pumice-rich basalt, a really dynamic rock, and look the contact with the massive sulfides. This is not an oceanic bottom. You cannot form this in a bottom, really active mass flows. There is no place, there is no time for forming a massive sulfide on the seafloor. The only way of interpreting this is their replacements. And the interpretation we have, if they were glassy rocks, really porous, really reactive, and fluids coming upwards, they don't need to go to the surface of the sea. If they arrive to a beautiful aquifer or fluid mixing that can take place, they just replace the volcanic rock. In fact, some drilling are doing the Japanese today. They are finding that below the thermal system in the Okinawa throat, there is hundreds of meters of massive sulfides. So perhaps the second lesson today is massive sulfides don't need to form on the seafloor. They can form below the seafloor, just finding reactive rocks or glassy rocks that can be replaced very, very easy. So two very different styles of mineralization. So at the present day, that's the description. We have too many questions, very few answers. The Pi is one of the best studied belts in the world. We don't know if there is any relationship with magmatic hydrothermal fluids. What's the influence of the continental basement? That's somewhat unique in VMS systems, to have a continental basement on the VMS. We have this strange link with the Devonian Carboniferous boundary. And also, what's the relationship between styles of mineralization? Some numbers, some geochemistry. We leave the field for a few months. As I said, what makes different the Pyrite Belt from other VMS districts in the world are the salinity of the fluids. If you make a study of VMS deposits in the world, you will find that most of them is just convected seawater. That means seawater gets into fractures, goes down, it hits, and then it comes upwards along faults and forms the vents in the seafloor. That's the classical model. In the Pyrite Belt, salinities are extremely, much higher, 12-15%, nothing to do with seawater has 3%. These high salinities, two alternatives only. Magmatic fluids that have solved and have had phase separation of geocentric waters that have accumulated with sedimentary rocks. How we can know that? Isotopes. Let's do some isotopes, big cows, nothing definitive. Magmatic waters should be around here, metamorphic waters here, we are all around there. It could be magmatic, it could be metamorphic, it could be sedimentary. Isotopes, stable isotopes, don't help a lot. Strontium isotopes. Now I'm going to sell, for us, radiogenic isotopes. Biogenic isotopes are absolutely great for solving these problems. And one amazing thing is that people working in our deposits, they usually don't use biogenic isotopes. And biogenic isotopes are absolutely great for solving metallogenic problems. They trace perfectly the origin. You are probably in one of the best places in the world for doing biogenic isotopes. Take advantage of the labs here because they solve a huge amount of problems. Here we have oxygen, stable isotope, versus radiogenic, versus strontium. More radiogenic, less radiogenic. We have the rocks in Tarsis, the rocks in Neves Corvo. We have seawater, mafic rocks in the Pyrite Belt, felsic rocks in the Pyrite Belt, and the shale in the PQ group. What we can say from here? Clearly, the ore doesn't come from the volcanic rocks. We have extremely radiogenic strontium. It doesn't come from the volcanic rocks, even from the felsics, even from the mafics, absolutely impossible. It's not seawater. It's not seawater. The only alternative is the PQ group, the basement, that continental basement we have below the VMS. And even so, some of the massive sulfides have more strontium or more strontium-87 than even any shale in the PQ group. That means that fluids were equilibrated with a more radiogenic source. And the only possible alternative is the basement. So fluids are not equilibrated with igneous rocks, and they are equilibrated with sediments. And that's consistent with the osmium isotopes, really crustal signatures, and with the lead isotopes. So, as a major difference with other VMS districts in the world, the Pyrite Belt, the fluids are equilibrated with silticlastic or continental basement. It's not equilibrated with the igneous rocks. In brief, well, that's probably a bit repetition of what we have said. Conclusion, our fluids are exactly the same fluids you find in VMS, in sedimentary exhalative systems. And this is perhaps consistent with what we see in the field. Sometimes you don't need to make a lot of numbers, you have only to walk around. That's not the Pyrite Belt, that's the Andes, but that's classical magmatic hydrothermal system. Look at the huge amount of alteration you see. Here in the Pyrite Belt you don't see, there are igneous rocks, but you don't see these huge magmatic hydrothermal systems. Alteration is really, really small. Another argument for saying that the source of metals are the sediments is, in brief, if you compare the copper, zinc, lead ratios of the deposits with those of the different rocks, you will see that they fit quite exactly with the sediments, suggesting that copper, zinc, and lead come from sediments. And what about the sulfur? People love to use the sulfur isotopes. What does sulfur says? Again, we don't need sulfur isotopes to see geology. And what we see is that the stockworks, remember, have very high contents in sulfides that we don't find in the massive sulfides. And these sulfides are formed at low sulfur fugacities, low sulfur contents. That means arsenopyrite, cobaltite, pyrrhotite, tellurium minerals, gold, and so on. And the second thing we see is that the stockwork have values close to 0, but the massive sulfides have below almost -20, -30 to 0. Negative, very negative sulfur isotopes. Very negative sulfur isotopes only mean biogenic activity. So, in brief, we have one sulfur that comes from the basement, with the fluids, with the metals, have a value between, let's say, between 0 and 10 per mil. And in the storework, this system has very little amounts of sulfur. Sulfides, the sulfides you precipitate are sulfides that don't have a lot of sulfur. And then they arrive to the seafloor, and in the seafloor, there's huge amount of sulfur. They precipitate the normal minerals, pyrite, sphalerite, galena, and so on. And this sulfur has very negative values. Very negative values, as you know, means bacteria. So we have deep sulfur from the basement mixed with bacteria. We're getting a bit late, so. Why we have little sulfur in these deep fluids? Having low sulfur in the deep fluids means that metals can be transported very quickly, very easily. If you have a lot of sulfur in a fluid, sulfides will precipitate very quickly. So a way of not precipitating sulfides is to have low sulfur. If you have low sulfur, metals can travel a lot, no problem, till they find a place where they have a lot of sulfur. This is a problem as every world of opportunities. Metals are looking around for sulfur to form sulfides. They prefer to stay as sulfides and not travel all their life looking around for sulfides. So when they find sulfides, they're really happy and they form massive sulfides. If they don't find sulfur, they continue traveling and traveling till they find sulfides. So the problem is how we can form a fluid that's rich in metals but poor in sulfur. That is a big debate now when working in deposit systems with high metals, low sulfur. How can we produce these strange rocks? Probably the explanation, let's go. Explanation is here. Redox, oxidized systems, reduced systems, that's ppms, and that's the solubility of a normal fluid equilibrated with a shale at 300 degrees. And that's the scale of the solubility is logarithmic. See what happens with the zinc, with the iron, with the lead, and with the sulfur. Straight line coming down. That means in extremely reduced systems, that way, you cannot transport metals. In very oxidized systems or intermediate oxidized systems, you can transport a lot of metals, but you don't transport sulfur. So if you have a fluid and equilibrated with shale, you can transport a lot of metals and very little sulfur. So probably that's the situation we have. A fluid equilibrated with shale leaches all the metals from the system, but leaves the sulfur behind. And it can travel all the crust around till it arrives to the seafloor. And when it arrives to the seafloor, it says a lot of bacteria producing sulfur and precipitating it there. Let's pass. Almost finishing. We've done some numerical modeling trying to explain this. And amazingly, what we have seen is that if you think of a continental shelf, shale, sandstone, a very thick sequence, it's full of water, probably 40% of water. This water is saline, it's typical basinal fluids. And suddenly we produce a basin, and there is an increase of the heat, and that's what the numerical model plans to do. What happens? Well, the first fluids that form in the system, the very first fluids are extremely saline, and they come from the basin. So in the convection, the first fluids are hot and saline, and they last for 1 million years, exactly the same age we obtained for the massive sulfides. And later on, the system is recharged by seawater, cooler and less saline, and that doesn't transport any metals. So our interpretation now is that just heating of a sedimentary sequence will produce a very short snapshot of highly saline metal-bearing fluids that come to the seafloor, and these form the VMS deposits of the southern Pyrite Belt. Afterwards, the convective system is recharged by seawater, and this seawater is cooler and less saline. You cannot transport any metals. That's what forms the manganese deposits and the shells that we have in the upper part of the belt. So, for one time, looks like numerical models fit into what we see in geology. Well, I've explained more the brine pools. People just remember this thing of VMS deposits replacing. The seafloor is there. Again, fluids don't need to go to the seafloor. VMS deposits not always form on the seafloor. They can be replacement. They can be replaced if they have beautiful glassy rocks saturated in water. They replace the glassy rocks. They don't need to go to the surface. Many massive sulfides, and especially the largest ones now in the world, are formed by replacement. Because if you replace, they don't oxidize, they don't get eroded, they are inside the volcanic sequence, so they are have much more chances of being preserved. So what explains the Pyrite Belt is basically only a few things. First, a reservoir with a lot of fluids hosted by sediments. High heat flow that makes all these fluids circulate and go to the surface, having small basins where you can concentrate the massive sulfides, and input of external sulfur. Which kind of external sulfur? Bacteria. I think that's, you can read all this stuff. I'm getting really late. We'll give you a PDF. So just remember, Pyrite Belt, important place in the world, pull apart continental basin. Major difference with other VMS districts is the relationship with acidiclastic basement. These fluids are low sulfur, high metals. They react with the seawater in the seafloor, and this seawater is full of H2S produced by bacteria. We don't need magmas to form these deposits, but they are there. Probably it's only heat, and probably this model could work for other VMS in the world. So I think that, yeah, that's it. Thanks. So perhaps I've been a little too quick, but I was looking.
Professor,
I will repeat again.
thanks for your time, but do you have any time for questions then?
Me, absolutely. It's not you if you are not very tired.
Oh, no.
All of you have to go on strike.
Okay. Okay, so do you have any questions for? Today?
I have a question. You said that source of sulfur is the source of sulfur is the bacterial reduction.
We think so.
But when we work with sulfur isotopes, sometimes the fields of the ratios are superimposed, magnetic and material and seawater. How do you do this interpretation of bacterial reduction?
If you could do a terrible question, that's it. Sulfur isotopes are really tricky. Because, for example, if you say a value close to 0 per mole, people say they are magmatic. They could be magmatic, but they could not be magmatic. I mean, it can be a melt absorbing sulfur, but it could be also and igneous rocks where sulfur has been leached from the geophysical source. In the case of bacteria, negative sulfur isotopes, they prove they are bacteria. But non-negative sulfur isotope don't mean that you don't have bacteria. You understand? So you see a value of -30, you say bacteria. If you see a value of +10, you cannot say there are not bacteria around. You understand? So it's really how to prove bacteria are around here. The arguments are three. One is that we have found biomarkers of bacteria. That means the bacteria, when they die, the membrane, the cell wall, has a lot of lipids. Lipids are well preserved, and if you leach the organic matter from the shell, you extract it with dissolvents, and then you do gas chromatography, you can obtain a signature that is lipids of bacteria. That's the proof. I mean, if you find that, you have bacteria in your system. That's probably the only really definitive proof for bacteria in a system. The second proof I will use is carbon isotopes. If you have carbon isotopes below, let's say, -15, -20, that means bacterial oxidation of methane of hydrocarbons. No other geological process can form very low carbon isotopes. Less than -30, bacteria. And sulfur isotopes only in the case that you have very negative ones, you can guarantee that they are bacteria. But if you have positive ones, you can also have bacteria, but you don't see it. So it's a bit tricky. In fact, biologists working on sulfur isotopes are rather impressed with geologists saying systematically that negative sulfur isotopes means bacteria. For them, bacteria do everything. Sometimes they fractionate, sometimes they don't fractionate. It depends on the amount of food they have, the type of food they have, the type of bacteria. Answer the question.
Yeah, it was.
Sulfur isotopes help, but they are not definitive, let's say.
Yes, you have to combine a lot of.
Yes, you have to combine it. And also the common sense, once more. I mean, probably in geology, you don't need to make a lot of numbers to think about things. I mean, what I showed, stonework has low sulfur minerals. The massive sulfides have a lot of minerals, they are very rich in sulfur. That means sulfur has to be in situ, it cannot come from the deep fluids, it has to be there. How can you form a lot of reduced sulfur on a seafloor? Only on an oxide bottom. You have to have stable sulfur, and you have to have, and the way of producing sulfur in an oxide bottom is just bacteria. You don't have any other alternatives. So many times, numbers help you to prove your geological model. But you have to have an idea just from geology before getting into numbers. There is always a diagram that proves what you want.
Professor, I have a question.
Professor.
Fernando has a question.
Thanks.
I do not study VMS deposits. I'm more of the porphyry thermal family deposits, but I would expect lower salinities when considering ocean water. So I believe the basinal fluids are essential for the formation of the transportation of the metals. I just want to ask, which source of studies do you guys perform to establish the salinity of the fluids? Was that fluid inclusions? Was that?
Wow, you are well trained to make tricky questions. No? One of the major problems working in VMS deposits are the fluid inclusions. Think if you're working on porphyries, on epithermal, you're working with well-formed quartz crystals forming at high temperatures, so you can assume that the fluid inclusions are primary ones. Then you go, imagine to these rocks, they are formed close to the seafloor, and they precipitate by very quick saturation. So the chances of forming good hydro crystals are really small. So probably quartz that precipitated here was first in the form of fine-grained jasper or silica, or what you call it, what you want to call it. No? And then afterwards crystallizes. So the fluid inclusion you're measuring is a fluid inclusion related with the original fluid, is related to the genesis, or is related to metamorphism. Personally, I don't trust a lot all these fluid inclusion data. And I don't trust most of the fluid inclusion data in VMS deposits or systems. But people use them, and people argue that they are primary. And by the way, they are perfect for our model. But honestly, if somebody makes some stuff in the Pyrite Belt on a VMS district and says that all these fluid inclusions are bullshit, I would say I would agree.
Okay.
That was a really good question.
Do you have another question? So, I believe we're done. Thanks a lot, Professor, again, for your time, and feel free to come back anytime to University of São Paulo.
Thank you very much.